bit about I2C pull-up resistors. And in this video I will be taking care of some of the left for later, but I will try to fix as many as I can. Let's see. C45. Let's see. There we go. So this one is why was this a yellow item? See, this is the problem with yellow items. Like, for some reason I marked this as a yellow item, but I didn't write down why. So now I have to figure out why. And this one is a 10 microfarad capacitor, which is used for our 5 volt regulator. At first, my first impression is that it's too small for this, because there is also a connector that may connect to something external. But I think maybe so I got 220 and I got the 100 microfarads. I think what I'll do is just I'll keep that one and I'll just add another one like this. So let's put an aluminum capacitor here. .25 volts. That's perfect. Maybe this was something about let's see, 5. Yeah, it seems correct. So I don't know what was the main reason I marked this as yellow. Let's see. There we go. This one is 603. So that's actually wrong. It's 603, right? But why is this 805? C45, yeah. 10 microfarad, 35 volts. Okay. Let's see, is this the... No, that's not the same one. Okay. So this one is 25 volts. And the other one is 35 volts. Yeah, and they are supposed to be, say, ten microfarad, 25 volts, 805. And so where is this one present? So if I open it, let's see. So I open it with the library editor and I get 25 volts, 805. Right. But if I search for this, yeah, maybe I had the wrong, let's see. Right, 73L. So I must have changed this capacitor to 25 volts. It's quite possible that the one that's there now is 25 volt capacitor. Yeah, I really have to take care of all these yellow items because otherwise I'll just forget the small details that relate to them. So it's 805, yeah, 25 volts, okay. I'm gonna keep that one, let's make it green, and then we have 100 volts, C89. So let's just go and search for C89 here. This one was the CP1 and CP2. Right, I chose to keep this one at 100 volts because I couldn't find any information on what voltage that capacitor should be. So so I yellowed it, but it's a 603, and let's see. Yeah, and it's this article number. Yeah, 603, 100 volts. Let's keep them at 100 volts because I remember I was going to come back to this and see if I could change them to some lower value in voltage, but I'm going to just read them and keep them at 100 volts. So R109. Right, so in this case it is recommended that one uses an external pull down because even though this chip has internal pull downs on the address lines, they're of such high resistance that there can be noise that enters the chip, and the noise can inadvertently toggle one of the address lines and make the chip unresponsive to the I2C address that's being used for that chip. So pulling them down is a good idea. This is one way to do it. But I think that for all I2C chips, I really the best approach would be to allow selecting the address. But it's kind of like, it would require more components. And one way here is to make sure that there are no conflicts on the I2C interfaces. So I made a note, I think somewhere here, to check everything that connects to the I2C interface for any conflicts. So we have, let's see, APSDA, EESDA. Yeah, so there is a LED controller, there's EEPROM, and then there are two two of these. Let's see. I think this one is, yeah, this is mock PSDA, and a PSDA is actually this one. This one, yeah. This is analog out, and they need to have different address. So if this one is connected to ground, then we need to make sure that the other one is connected to VCC. Let's see. That one here, yes. So this one is connected to VDD33 on A0, so they should have different address. Now, these two resistors, 78 and 79, I don't know why I put them there. I remember having a reason to put them there, but when I think about it, I think that as far as I can remember, I had some idea that what if the chip doesn't work, and I have to have some resistor going to VDD, and the way I kind of this is kind of like a workaround. So this is a bypass for the overcurrent adjustment. But then the question is whether we actually need it, because we have the possibility to turn off the overcurrent adjustment completely in order to be able to use the Rev A board, and that is done by just connecting this output to a GPIO pin as well, which can drive it high in case it is necessary to adjust the overcurrent set point. But then we get into the problem that maybe like how does this chip actually respond when you feed current into the wiper pin, or like it's kind of like an output, but I'm not sure exactly how that works with this digital potentiometer, whether it's possible to, like, for example, what happens if you're driving this pin high and you've set the resistance to something really low, so that this pin is kind of shorted to ground. That may destroy the chip itself. So one approach to do this is to actually have resistors here, and what we can do with them is actually make them no fit, so that we still have the possibility to bypass this overcurrent set point, but we don't need to have those resistors mounted. I will still keep the GPIO pin, but I will make it probably something like open drain or something, just to make sure that yeah, I will probably actually have a resistor going to that GPIO pin or something, or I'll just if this doesn't work, then I'll just solder a 0 ohm resistor here, and by doing so I will get no overcurrent protection on the drive, so that it will work. So actually, if I use these resistors, I don't need to also connect the OC adjustment to any GPIO pins, so I can remove that. Let's see. Okay, so this does not need to be connected. We have OC edge 1 and OC edge 1, which is wrong. This should be OC adjustment 2, which is why it's a good idea to also go over all the labels later. Let's see, edge 1, edge 2, edge 1, edge 1, edge 2, edge 2, and adjustment 1 is there, so remove that one. And actually GPX reset pin can then go here, because now it's makes pretty good sense to put it there, because it comes with other pins that go to GPX. Alright, so this is fixed, and I can green light these two resistors, 78 and 79. Let's see, R78 and 79. So these two will be green, and then for the EEPROM, you can do like this. So like for this EEPROM, let's see here. So this EEPROM will just be connected with address pins to ground. This resistor is absolutely not necessary. So we can just go like this. What this means is that we won't be able to kind of connect a probe to one of these pins and pull all of them high in case there's a conflict and we need to debug this. But I think this is the only chip on this bus, so I'll just put it to address 0, and that would be fine. Now there are other I2C addresses. So this was 109, I think, right? Let's see. So this one was green. There are no other yellow labels. So I'll go down to the next 129. Let's see. Resistor 129. What is 129? Right. So these ones are pull-up resistors for this I2C bus, 129 and 130. And I think that's pretty reasonable to use a 3K resistor. We could use 5K, but yeah, 3K is fine. Let's see. So 149 is the next one. So because these pins are open drain, it's good to have pull-up resistors that are kind of like on the lower side, but not too low. So that you get like a very much sharper rise time on these pins, and that allows to run the I2C bus at a higher speed. So 149, then next one. Let's see. $149 is for this. For this. So 149 and 160, I'm going to keep them yellow right now because I want to go over this schematic again when I have the data sheet of this chip, and I have to read through the data sheet a little bit better before I review this whole component here, because there can be things that I've missed in the data sheet, and I basically just feel that I need to to read the datasheet in more detail so that I can see if there are any other problems here. So I'll leave the resistors for the time when I'm going to go through that. And I'll move to R34 here. That one was right. So this was actually wrong because the chips have pull-down resistors. So it doesn't matter if we have resistors here. It would be better if I had resistors that go both to the ground and up to the let's see. Although what is this A anyway? Let's see, MCP 23517. I'm gonna open up the datasheet. I could probably do it like this. It could be that this address is for I think the chip supports both I2C and SPI, but let me check. By the original high-speed SPI interface, high-speed I2C interface. So 23017 is I2C, and we have S17, so we have SPI. Now it's actually quite possible that these pins are not connected. Let's see. So S17. So what is A0 on S17? Must be externally. Okay. The slave address contains 4 fixed bits and 3 user-defined hardware address bits. Right, so this seems to be that it's possible to address them even in SPI mode. But it doesn't really make sense to put any resistors here. So 34, 35 and 36 will go away and be replaced with just wires. Because we're using 2 different CS pins. The same thing for 43, 44 and 45. Okay. Yeah, so that was the main bulk of the yellow lines. Let's continue with R58. R58 is here, and it's 147K. 603, yeah. $147K. 37k on. Yeah, we can green that one. And then there is 24k R59. Also 603. And 4k 603. Great. Let's see. Let's make that one also green. And there is another thing which I looked at in the previous video, where I made an erroneous calculation for the current through these resistors. It didn't quite make sense to me, but I didn't really know how to calculate the current through this resistor, because the MOSFET acts like a capacitor, so it's kind of like it's going to be a current spike, and then it will be pretty much going to zero. So what I did was I just simulated it, and that gave me a good answer. So the more gate charge there is, the more current is needed to charge it. So I chose a MOSFET that is the IRF 1310, which has a higher gate charge than the MOSFETs that I'm using, and this is what it looks like when there is a pulse of 10 volts going through a resistor and charging the gate. And the current is always under 1 milliamps. We can also try making this 60 volts, and we can see what the current is going to be here. So we got, let's say we got 6 milliamps. Now even if we have 6 milliamps, then the power dissipated by the resistor is this current times the resistance, which is in this case 22 ohms. So it's going to be 0.7 milliwatts, which is well within the range of the 402 parts. We can check actually the 402 part can take. So 603 part is 100 milliwatts. So 402 is probably like, let's see, we can actually take this part. Let's see. 62 milliwatts. So according to this simulation, there is plenty of room to make sure that this resistor doesn't get hot. So I'll leave that topic for now, and I'll move on to the next resistor on this list. That'll be R60. R60 is 10k resistor on boot 1 pin, which is supposed to be connected to ground. So we can bring that one. And we have another R61, is the 10 milliohm resistor, which I think is right here. Yep, R61. It's the same 10 milliohm resistor as the other one, this one. R62, what's that? R62. Let's see. So this basically enables this regulator. Yeah. So this is just going to be high level on the enable pin, which is fine. Can bring that one. R63 is that. That's the address of this one. So this is button LEDs. And once again, if I wanted to pick the address, I would have to have resistor dividers with one side mounted and the other one marked as no fit. LP55231. Let's see what address it has. Maybe we can open the datasheet right away here. No, there was no datasheet. So 32H is the default one. Let's see, and so BLED is 32H. We can copy this one. Actually, we can just set this. Let's see. And what about the other one? Let's see. So is this like 40? Let's see. Right, now this was the GPIO expansion. I wonder where I had this. Let's see. Let's open the datasheet for this one. So what is the default address? Okay. So we've got let's see, 8, 9, A, so B. Let's see, or actually no, it's 50, and then the thing is, sometimes they specify addresses as just this part, or as the whole thing. So I think I will use the convention on the schematic to specify addresses as the whole byte, but without the read-write bit. So in this case, it would be if both are 0, it would be 58. And it can also be 55. So this one is G and G and G and D. And this one has A0 set to 1. So we can modify this and set AP is 58 and mod P is 55. And what about the EEPROM? And also here, I will connect these to ground. Because they have very weak pull-down resistors. Yeah, this one becomes A0. Okay, so we can delete this one. We have the I2C addresses, and then this was let's see, R63 and 64. Which yeah, okay. So we can just remove them and connect this to ground. All right. R65. So there. Looking good. R66. That one is used to select SPI mode. Question is if we need it. Max 14,890. Let's see. Right, its SDO is okay. Let's see. SPI high or low? Yeah, we don't need a resistor there. This can basically be just connected to this VDD source. So R66 can be green, and got R67 then. Oh, that was... Let's see. That's a good question, actually. So should it be using 5 volts VCC or the VL? Right, to 6 volts. So we can actually set this SPI pin to 5 volts. This can be VCC instead. And that kind of avoids the possibility that this pin may not respond to 3.3 volts. So R67 is also going to be greened. So I'll move this 5 volts label there. Right. It's only a few resistors left. R70. The only thing about this 270R, I think, unless I already greened one of them, just check whether this is correct footprint. Yeah, it's supposed to be 402. It's kind of obvious by the article number. 270R. Also that it's 270R. So we can green R70, 71, 72, 73, 74, 75. And then there is R76. So R76 connects the output of this op-amp to the input of the ADC. And R76 is not actually needed because we're not using higher voltages here. This is never going to exceed 3.3 volts. So this can just be connected directly. R77. That's interesting. Okay, so that's the bias. 12.1K. 12K1 402. Yeah. Can green that one. And then there is R80. So R80 goes through 1.5K resistor, which is kind of designed to limit the current that flows through here. And into the VDD33 supply. I think we should make this 3K. I think 1.5K is too little. Yeah. R80 and R81 can be greened. And then there is R82. and 83, R84, these are pull-ups for the open drain outputs, which is correct, 485, and probably 86, 87 then. Yeah. 587, 84, 86, 85, 87. Yes. Green and then 49. That's also green. 492. One mega ohm 402. Yep. So I'm done with the resistors. Now we have a few switches, test points, and then ICs. That's the